Quantum computers are demonstrating transformational capability in how we think about and what we will be able to do with computing. But there's a big challenge in creating an operating environment that enables a quantum processor to operate effectively. At SemiQon, Himadri, you've created a solution that allows a quantum machine to operate at much higher temperature, which sounds like not a big deal, but it actually is. So how does your chip compare to the state of the art that's out there today?
So with quantum computing, we are currently at the stage of big room full of computers in a way. And that requires a lot of infrastructure, predominantly because of the cooling that is required. And when we talk about cooling, we talk about temperatures which are, let's say, 1,000,000 times lower than the room temperature in a way. So it's incredibly difficult to get to that point. And at SemiQon, what we are trying to do is bring that infrastructure down and make it operable at temperatures which are equivalent to space temperature. And that reduces the cost of infrastructure, that reduces the size of infrastructure, and at the same time, using silicon as a platform makes it possible to do the manufacturing using available infrastructure. So the cost also goes down in terms of production.
So from where you are today, with temperatures in the -250, -270 degrees centigrade range, outer space temperatures in order for the processor to operate, do you see a potential to get closer to room temperature?
At least getting towards that, yes. And if that is not the case, because those are material dependent characteristics, so how less noise we can do. The other way of looking at it is bring the cryogenic volume lower.
So if you can have the fridge smaller.
Exactly. So if you can make cooling on a chip, that would bring the cooling on the chip. And that's how we can potentially address that problem. But we believe in SemiQon that room temperature quantum computing is very difficult.
The SemiQon processor is going to be able to use silicon and use existing manufacturing fabrication facilities. That's going to be a huge advantage. Do you see yourself as a competitor long-term to the big chip manufacturers, or are you a partner?
At this point of time, the race is on the know-how. So whoever develops the IP quicker and better. And eventually, this becomes an activity which requires a lot of investment. So as a company, at some point, we will have this strategic discussion whether we build our own infrastructure and build the facility to do it, or we partner with a larger fab. At this point of time, I think that's the easier way to do it. So tech transfer and let them do that.
When you talk about this midpoint, this transition point, do you envision machines where once you're able to shrink the cooling sufficiently, you buy an integrated circuit with a traditional processor and a semi-quantum processor on the same computer board?
That would be the dream, yes. But we have to keep in mind that the current production facilities have their own way of doing things. So if we transform things too much, they won't be able to handle it, and that costs money. So we are trying to build the things exactly the way the traditional semiconductor industry works.
Yeah, follow their processes.
Exactly.
From what you see today, what are the applications of the quantum computer that you're most excited about?
From an application point of view, the quantum computers that we see nowadays from various different vendors, they are fantastic because they are proving the point of quantum computing. They are showing things that are possible with quantum computing.
But very different approaches in technology.
That is correct. That is correct. But the goal is to do quantum computing with whatever technology is being used. And what they are showing is it's possible to do some incredible things, but they are not able to show things that classical computers cannot do. So we are looking at an era in the future where we call the quantum advantage. That means things that quantum computer can do, but classical computers cannot do. And that requires a lot more powerful quantum computers. And that is exactly what we are building. And our goal is longer term.
So what will be the first application we'll see on a SemiQon quantum machine?
We hope this will be, there are various different application domains which are being tried right now. And some of the most promising ones are how you design molecules, pharmaceutical molecules, for example.
Drug discovery.
Correct. The other application is logistics, how we can do better logistics, get the things done quicker.
In terms of optimization problems.
Exactly. There are many such. So optimization is a general mathematical problem that can be addressed.
Yeah, in many industries.
Exactly. The challenge right now is, as I said, going to the quantum advantage, and that's hard. So what we are seeing now is an intermediate state where quantum classical hybrid is going to happen. So for example, if you have a computation that you do in a supercomputer, for example, that takes a day to complete, with having quantum on the side, you might do it in half a day. That's a huge business advantage,
Right.
not necessarily a quantum advantage. But that's the starting point to do those things.